In this video, we're going to discuss the binomial distribution. The binomial probability distribution is still a discrete probability distribution, but it describes probability experiments in which there are only two possible outcomes, and these outcomes must be mutually exclusive. Remember, mutually exclusive means that there is no overlap in the possible outcomes. They are to the point where they do not occur at the same time in any shape or form. For these binomial probability distributions, we have different trials. And what these trials are is just how many times do we run the experiment, the repetitions of the experiment. And so there are certain conditions that must be satisfied for binomial distributions. First is that there must be a fixed number of trials to be conducted. We can't say after the experiment starts, oh, well, we're going to change the number of trials. The number of trials must be fixed in order for us to know what we're dealing with. Also, there are only two possible outcomes for each trial, and we denote these with either it being a success or a failure. And so we have to be careful with our success and our failure because it depends on what we are looking for. If whatever we are looking for, that is our success. And then the opposite of it is our failure. So like flipping a coin, if we want heads, then heads is going to be our success. Tails will be our failure. But if someone else is running the same type of experiment, maybe they want tails. So in their case, tails would be considered a success. So you have to look at how the experiment is written and what is actually deemed a success. The probability of a success is the same for each trial, meaning each trial is independent of each other, which is condition number 4. The probabilities do not change from trial to trial. This would mean that from one trial to the next, we cannot alter those probabilities at any point. And our x, of course, is going to represent our number of successes. And so other notation, of course, I can put down here x equals number of successes. And so n is going to be our number of trials, how many total we're looking at. P is going to be the probability of our successes. And so the opposite of that, 1 minus P, is going to be the number, or the probability of failure. And so let's look and see if we can determine which of the following are binomial random variables. And so when you're trying to determine, basically you're asking, does it have only two possible outcomes, or are there multiple outcomes? And do the probabilities stay the same? And so for the first one, we have an experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws. And the number of free throws made is recorded. So here, do we have a fixed number of trials? Well, yes. Our fixed number of trials is 3. So we have 3 for our n. Are there only two possible outcomes when we're discussing free throws? Yes, we either make the free throw or we miss the free throw. And since we are recording the number made, this is our success. Okay, we make the free throw. And then we ask, is our probability going to be the same through each time? Well, yes, because there's nothing to change the probability of the free throw being made. it's not like another set shot or anything, somebody blocking it. So the probability of making a free throw is always going to stay at 80% or 0.80. So yes, this is a binomial random distribution. Now looking at blood type O negative is based on a simple random sample, size 10 is recorded. According to the American Red Cross, 7% of the people in the United States have blood type O negative. So looking at this, are there two possible outcomes? Yes, there are. There's either O negative or you're not O negative. We have other types of blood type, but we're not asking those. We're just looking at, do you have blood type O negative or not? So this is considered our success, being O negative. And then we ask, do we have a set number of trials? Well, yes, we have 10. So N is 10. Now then, with blood type, it's not necessarily independent because, of course, your blood type is based on your parents and your family tree and everything. But if you go back to the rule of large numbers, we're talking about the whole population being the whole population of the United States. And we're only taking a sample size of 10. So that sample size is less than 5% of our population. And if you recall that when we take a sample size that's less than 5%, we automatically deem that the trials or the events are independent. So in this case, the trials are independent of each other because the sample size is less than 5% of the population. So yes, this is a binomial probability distribution. Now then, for this next one, a probability experiment in which 3 cards are drawn. So we do have a set number. We have a set number of trials. We have 3. They're drawn from a deck without replacement, and the number of aces is drawn. So we either have aces or not an ace. Okay, so this would be our success. This would be our not a success or our failure. The issue here is this without replacement. Because the probability of drawing that first card is 4 out of 52 for an ace. But if we draw a card and do not replace it, we now only have 53 cards to draw from. So our probability does not stay the same, and therefore the trials are not independent of each other. And both of those put together mean that this is not a binomial random variable because of the fact that our trials are not independent and our probability does not stay the same. Now then, when we're talking about binomials, remember that we have either a success or a failure. So look at some possible outcomes and see, can you determine whether it's a binomial or not? And if it's a binomial, can you pick out what is the success, what is the failure, what's the probability, what's the number of trials? And if you have questions, please let me know.